No, that's one I brought.
Oh, okay. No, you're good. You're good. I didn't know you brought it. I thought there was one up here.
No, I don't know. I think the one that was up here was Lucas's.
Oh, okay. That's fine.
Do you want me to open that?
What?
The mold up?
He's got it.
Oh, he already got it.
He should got it.
Should have. You ready? Good.
Yeah, on you.
All right. We are RPS for Recycled Plastic Structures. I'm Stephen Gazy. I'm Michael Czerkowski.
And I'm Owen Breisch.
So just a brief introduction and reminder of what our project is. Recycling is the #1 way here to take old garbage and to make it into something new. So our design for RPS is to take garbage and old plastics that haven't been recycled yet and put them into our machine, melt them down and put them into this mold and make modular bricks that are stackable and interlockable to be put together to make a building or a small structure that could be used for disaster relief or emergencies, stuff like that. Our bricks have been designed and we've been testing them to withstand the pressure of being able to be stacked up high enough to make a building or a small room. And this is a proof of concept that we are able to reuse PET plastics into something that could be used again. So this is just a quick breakdown of our schedule. In the fall semester, our main idea was getting the brick design to work by itself and having interlockable bricks that stack and fit together nicely. Where this semester we focused more on building the actual apparatus with the plunger in it and the actual testing to make sure that everything's working out and we're getting proper molds from the machine. This is also just our quick budget. The main part of our project was the heating bands to be able to melt the plastic down and the controllers for that. But also we came in pretty decently over here. We're under budget, so that's a success for us. So we do have extra money to spend because we did have one heating band break on us, so we had to order a new one. And we used some of that extra money as well to buy a heating pad to set the mold on top of. That way when the plastic is being put into the mold, it doesn't cool too rapidly, because that was a problem that we had early on in the beginning. So these are some previous designs that we had from when we started the project, and our goal was we kept it very similar to what we originally stood out for, of having the brick with the male and female cleat system on the end, and also having the studs on top with the holes on the bottom like a Lego brick. And that was also our first design of the apparatus itself, which is very similar to what we have today. And we're going to go to, Michael's going to talk about, or Owen's going to talk about the designs.
So kind of just going off of that, this is what our actual injection apparatus is. Up here on the far left, we have a picture of the actual SolidWorks model. This is kind of excluding all of the electronics to it. But you can see one thing that we added was we have slots for the PIDs, and we also have a slot for a light switch. Kind of just moving forward to the other two pictures, they show what the actual thing looks like with all the electronics, the light switch, the PIDs, and you can kind of see the wiring for the relays in the back. One thing to notice between the two actual real-life pictures is one has the blue kind of cover on it. That is a barrel shield. We'll get to that later. And yeah, this is kind of a setup for when we would actually be trying to push into the mold. So the second part of our project was the mold itself. It is comprised of 3 different parts. So as you can see, we have the SolidWorks model above, with the piece on the far left being our universal female, and the other 2 pieces connect into it using steel pins. And then you can see below each of the model pieces is their respective real-life counterpart. The pictures are looks a little crusty because that was after we pushed some plastic into it, but did the best we can with that one. So we know one of the major concerns from the fall was safety, so we kind of really wanted to add that slide into our presentation. One of the first and main things is just gloves. If we're working anywhere near the barrel and just kind of we're close to the contact with anything hot, we want to just make sure we have them on. Additionally, I mentioned before the shield, the bright blue thing on the front of the apparatus. We have a picture of us temp gunning the shield there. So that's running around 160 degrees Fahrenheit compared to the barrel. That's like 500 degrees Fahrenheit. So I'd much rather brush against that than the actual barrel. But in addition to that, we added a few electrical parts to it. So we have the system on and off switch, which was just general safety, and then we were always plugged into a surge protector. And lastly, we did it in a room with ventilation, which was also important.
So moving along to our testing categories, what we first wanted to test was the electrical components, just to make sure that everything was communicating with each other, all of our heating bands were working properly. And once we got everything put together, we went on to our temperature control testing, which we started at about 500 degrees and went a little up and down from there to see like what was the best temperature, what results we got. So we took 500 as our good point for melting the plastic into the mold and then filling it out nicely. After we did that, we also went on to the mechanical testing where we put the plunger and everything together and made sure everything's flowing properly, everything's getting into the mold, there's no bubbles, just the physical aspect of the mold itself.
Electrical testing. Here we have basic circuit setup confirmation. The circuit's right over there, very simple, not like past projects are just up here, just a couple of PIDs and relays. Here's a chart showing what we tested and passed. The two things that didn't pass were the 1-inch heating bands and the heating pad that we plan to put on the mold. Picture up here is that first heating band. It burns up as soon as we powered it on. Not good. And that heating pad there, it's only about 1 inch by 2 inches, actually really small. They said that it would have been able to provide the right amount of wattage, but it just didn't permeate through the mold at all. And an honorable mention for the first setup confirmation was a blown relay. We shorted it out and it didn't work after that. Temperature control testing. We have a couple pictures of the PIDs, a hot plate, and that picture on the far right is the temp gun showing the heat distribution of the mold on the hot plate. You can see that it's providing enough heat through the bottom of it. We set up the 3 PIDs to control each section. We have we were going to put one on the mold down at the bottom, but as we said, the heating pad didn't work, so we went to a hot plate, which we didn't use the PID for. And this nozzle down here is controlled separately from the barrel, and that provides us with more variability so that we can keep them at 2 different temperatures and control them separately. Just right here is a little bit of an explanation of our testing and where it led us to for the mechanical section. The barrel, we decided we were going to mess with spacing. The nozzle, we moved to a 3-inch heating band because the 1-inch heating band didn't have enough wattage going through it, and the mold, we went to a hot plate.
So kind of like Michael was saying, when we're jumping into our mechanical design, we did do a bunch of different configurations with heating bands. This doesn't just include kind of testing them their temperature-wise, it was kind of their placement on the barrel. We had 2 of them very close together, and when we added a third onto the barrel, we kind of spreaded them out to hopefully get a more uniform degrees across the barrel. In addition to that, like we said, our smaller heating band ended up burning up and the other one didn't work. So we kind of made a makeshift, as you can see, we made a little makeshift spacer so that the 3-inch heating band would heat up the nozzle. So going off of that, we also had issues with the plunger. It is aluminum versus our barrel, which is steel. So when we originally had it turned, it would still fit in, but once it started heating up, it would expand and get stuck in the barrel. That was a setback for us. But now it does fit, and barrel, it does also have a little bit of non-uniformity to it, so it's not completely circular, so we also contribute that to a little bit of our issues with turning the plunger. Next, we do have stand stability. Once we kind of initially made it, we didn't have feet on the front, but we kind of realized it will be a little front heavy with the heavy steel shielding and the barrel in front, so we added small feet. And then last but not least, we did nozzle length adjustments. It was originally like 2 inches longer, but we were realizing we weren't getting enough heat to the tip of the nozzle, so we just pretty much chopped it around an inch or so off. So kind of what our procedure was on the day that we planned to hopefully inject something. We would start by kind of loading the barrel up with however much PET or plastic that we decided was enough. From there, we would then plug in the heat injection apparatus in the hot plate. From there, we would then set the hot plate to our preferred temperature, which was setting 1 or 2 around 300 degrees. And then we would set our barrel inner nozzle to around that 180 to 200 degrees Celsius range. We would wait for that to kind of reach that set point and stabilize. From there, we'd kind of push the barrel temperature up to our final range of 240 to 260. And once that got up to that temperature and stabilized, the nozzle was ready to kind of be switched into injection mode, which is around that 245 to 255 degrees Celsius range. So I guess what everybody's been waiting for, there were a few failures. So the 2 pictures on the left there, they kind of show, those are the instances where the plunger ended up getting stuck on the barrel, so we kind of just had to shut the whole thing off. And we came back the next day, and we have what we call like little pucks. You can see the picture on the top is a fairly melted piece, as opposed to the one below it, where you can see there's still actual plastic not melted. And then one of the better results is the picture right here. We got it into the mold, but the hot plate was a little too hot as we were trying to get the kind of the rest of the mold to heat up, and we ended up cooking it. But we did get a good 1/4 inch into the mold. But once PET is kind of overheated, it's extremely brittle and it loses all of its expected properties.
Here we have more melted plastic. You have some burnt stuff over here. There's a bunch of pucks that we had in the box there. One of the most important ones here is we soon realized that it was going to be very difficult to get into the mold, so we scaled it back a little bit, and we just wanted to get into a small cylinder that we put on the hot plate. And it wasn't quite up to temperature, but we got good penetration within the barrel, and we were able to push it out into the cylinder, and that's one of our better results, along with the one that was burnt inside the mold.
So kind of some of the setbacks, I mentioned a few of them already, and they were mentioned across the presentation. The plunger was a big one, and it stopped several different days on just doing anything for the rest of the day. We had issues with the heating bands, not only replacement, but some of them actually going up in smoke. Lone relay, it's the stand stability, stuff like that. Non-uniform plastic, another big one.
Coming to lessons learned, we learned a lot through our experiences. We did a lot of testing and a lot of varying the procedure, varying temperatures. There was a lot of work to be done in between test attempts too. So we've discovered that injection molding is quite intricate, and it was very hard to simplify and dumb down to something that we can bring within our means. And we may have shot for the moon on this one. However, things to do differently that would ensure a greater chance of success would be an aluminum barrel, because we noticed that it was hard to penetrate the cross-section of the barrel with our heating bands. Higher injection pressures, that would help with, if we got to an acceptable, it would lower our acceptable temperature a little bit, because we did often burn plastic. We're trying to get it within a certain range, and the range was actually surprisingly small once we started looking at it. And a more thorough sensing method for the PIDs. We just have the thermocouple welded onto, or 2 nuts welded onto the bottom of the barrel down here. And that's actually quite far from the rest of the heating bands. So heating bands would put a lot of heat into the barrel, and it doesn't transfer as well with a steel barrel versus an aluminum barrel. So we'd end up cooking the plastic up here, and the plastic down here isn't melted properly.
So kind of in conclusion, we were not really successful with what we set out to do, but we do think with some of the stuff we actually did get, it's fairly strong. We didn't do actually any testing on it. We don't have very good samples, but we think this is a good proof of concept for additional recycle applications, not strictly just like small bottles and stuff like that, something that could potentially bear some type of load or anything such as that.
In the end, we were unsuccessful. However, with more time and more variations with it, we probably could thread the needle and get a clean injection. However, we just weren't able to complete it with this semester.
This is a list of the resources that we used. We included that in our presentation. And we definitely want to put a thank you out to everybody at Wilkes for giving us this opportunity to create this project and work on it. We also want to thank Dr. Mu for being our advisor. We also want to thank Mitch Adams for his assistance building it and everything that he's done for us. And we also want to have a special thanks to Matt Haber and Caden Dearborn for their help and the contributions for this project. Does anybody have any questions?
So this project is very similar to the Phenom Max project, right? I mean, you guys similar, right?
Yeah.
Are you using the same kind of temperature heating device? Is that?
Yeah, we're using 3-inch heating fans that are rated at.
Because they have similar kind of caddy controller for the temperature
Yes,
control, right?
yes, that part is very similar. The main difference is usually is the actual method of they were doing extrusion while we were focusing on injection.
Yeah, I mean, like for this to even work, you see, you need, like for them, it's like they can't just melt slowly like a nozzle, but for you guys, you almost need a container to collect the melted and then inject at the same time. You can't just be like for them, gradually, you see what I mean, like just based on the temperature of the nozzle to try to.
Yeah, I mean, that was kind of the goal. We kind of tried to load it up, get it all to around a.
So that wasn't, because I guess it's because you don't have a heated container to collect it, keep it melted, right?
Yeah, that was kind of the goal for the hot plate, to kind of keep that mold.
Because that's like, to do that, that's lots of heat. That's
Yeah.
like a tremendous amount of energy there.
Yeah.
That might be the reason why it kind of broke down eventually.
Yeah.
How many water bottles did you have to melt down for the testing phase?
It was a lot. On any given attempt, it was between 30 and 50 water bottles. So 30 was about like 3 inches in the bottom of the barrel. So,
And they were all different brands. Did that give you any issues with
no,
consistency?
we cleaned them all pretty properly. We left them all very fine. And the material was very consistent.
Any other? Usually I have to kind of run on. Okay, thank you.